Hey everybody, coming at you today with the 4.2 Webwork guide. I know that this homework set is really tricky, and it's a section that's kind of in between ideas when we're going from areas under curves to eventually the fundamental theorem of calculus in section 4.3. So it can be really frustrating, especially when it gets placed over the Thanksgiving holiday. I'm really sorry about the way that's worked out in the schedule. It's just the way the calendar works. So because I feel bad about that, I'm going to help you get your web work done with this guide. So before we start on the web work prompts, I just want to quickly go over the ideas for this section. And the most important ideas come from the notes in remark 210 and definition 211. These are the calculations that set up the web work. Now first, what this remark is telling us are the calculations for the width of a rectangle in a Riemann sum when we're given the width of the interval or the interval endpoints and the number of rectangles, and the right-hand endpoint of the ith rectangle. Now, this is a little bit confusing, so let's just do this one step at a time. So what the first part A, is telling us is that if we have an interval from A to B, and we are splitting up this interval into n subintervals or n rectangles, that the width of one of these rectangles, delta x, can be calculated by doing b minus a over n. That makes sense, right? That's just the distance between b and a, and then we're dividing it by the number of rectangles that we have. So the width of one of the rectangles is given by b minus a over n. Okay, that makes sense. Now the second thing that we're trying to find is the right-hand endpoint of the ith rectangle. Well, it's a little bit confusing because it gets confusing what we mean by the ith rectangle. So let's write these down. So this first rectangle right here is the I equals 1 rectangle, and then the second rectangle is the I equals 2 rectangle, and the third rectangle is the I equals 3 rectangle, and in this case the fourth rectangle was the I equals 4 rectangle. Now what we're eventually doing is we're trying to build up the idea that we're going to have n rectangles, so that's why we want to index these things with n's and i's. When we talk about I as being inside of these n rectangles, that just means some random rectangle. So maybe it's the second rectangle, maybe it's the third rectangle. If we had 50 rectangles, maybe it's the 49th rectangle or that kind of thing. Now, arbitrarily, let's say that we're trying to find the ith endpoint. Right endpoint of the ith rectangle. So in this case, this would be the right endpoint of the third rectangle. But we want to be able to index this in terms of I. We want to be able to find the right endpoint for any rectangle. If I just give you an index, tell me the right endpoint of the 15th rectangle. What's the formula for getting that endpoint? Okay, so how are we going to find this third one? Well, we're going to start at A, right? And then we're going to jump over 1. Delta x is our unit there. We're jumping over one rectangle. Its width is delta x. Then we're jumping over a second rectangle. Its width is delta x. And then we're jumping over a third rectangle. Its width is delta x. So to get to the third endpoint, we would have done A plus 3 delta x. Okay, where delta x is a number, and we're making 3 of those jumps. Right? But if we wanted to go to the ith endpoint, we would be doing A plus I delta x. However many intervals we have, we're jumping over that many of those intervals to get to the ith interval, and then that's going to be our right-hand endpoint. We're starting at A. So that's what this A plus I delta x is. Okay. Now the last really important thing that we have to deal with is this very important definition that says that the definite interval, okay, so this is the definite interval right there, it is equal. It can be calculated by finding this series. Okay. Now, that's because right now we don't know how to do the antiderivative to calculate integrals. The integral is just something that we're saying is the area under the curve from A to B, and we don't know yet that we can just calculate it by finding the antiderivative, which is what we figure out in 4.3. But we can figure out this area by calculating a Riemann sum with an infinite number of rectangles, because then our estimate gets more and more accurate. All right, we have problem number 1 here, which is a weird problem to start with because we're actually doing the reverse process of actually calculating the integral. So in order to do that, I'm going to show you how we calculate the integral going in the forward direction, and then it'll be obvious to how we reverse engineer that to get the answer to this Webwork problem. So the answer to this question is that the function is the square root of x. Okay, so we have the square root of x as our function. Now let's say we were trying to calculate this using the definition above. Okay, so then this would be equal to the limit as n goes to infinity of the summation I equals 1 to n of the square root of x sub I and then delta x. Okay, now we know also that x sub I is equal to a plus I delta x, and delta x is equal to b minus a over n. So in this case, delta x is equal to 2 over n, because 9 minus 7 is 2, and x sub I is equal to 7 plus I times 2 over n, and oftentimes people will write that as 2i over n. Okay, that's our x sub I. So now our integral is equal to the limit as n goes to infinity of the summation I equals 1 to n of the square root of 7 plus 2i over n times 2 over n, and you'll see that is exactly the function that is given to us as our problem. And so therefore our answer is, well, this function that this sum represents must have been the square root of x. Now, that's weird. Like, why would we do a different problem to solve the answer to our Webwork problem? Well, we can do this without doing it backwards like that. The way that you do this is it's kind of like a search and destroy game. We're trying to figure out that, so what we have here is we have the limit as n goes to infinity of the summation I equals 1 to n of the square root of 7 plus 2i over n times 2 over n. So my search and destroy game here is that I need to find my x sub I, and I need to find my delta x within the function over here in order to know like how to simplify it out. So I can see here that this 2 over n, that's my delta x, okay? That equals 9 minus 7 over 2, or 9 minus 7 over n, that's my 2 over n. And that tells me that this thing right here, that must be I delta x, because it's just that 2 over n with an I in there. Okay, so I can do some simplification then. I can rewrite this as the summation I equals 1 to n, and I have the square root now. Okay, so I can like say this is 7 plus, all right, this is my I delta x right there, and then this thing on the outside is my delta x. Well, I know now that like this is my delta x part of my sum up there, and that this thing, so the delta x, there we go, I already have that found. Now this whole thing, that must be my f of x sub I. So if I can just tell like where my x sub I is in there, then like whatever's happening to it is my function. So like this connection here is that I know that my x sub I is equal to 7 plus 2i over n, because I can see in the problem statement that that's where my 2 is coming from, and I know that my a value is 7, so I can find my like x sub I right away. And that tells me then that, well, how do I get from x sub I to f of x sub I? Well, it's just being square rooted. So f of x sub I, we're taking the square root of what our x sub I is. Well, that just tells me then the f of x is the square root of x. That's kind of the way to reverse engineer it. So it's a little bit of a weird problem, but I think for everybody the answer for this first question is square root x. All right, let's take a look at number 2. For number 2, we're doing the exact same thing we did in the first problem, only we're doing it with a little bit different function, and our a values are changing and our like range is changing. Okay, so let's do it for part A first. Part A is the easiest. Okay, now there's some things that we're going to need to remember. We're going to need to remember that delta x is equal to b minus a over n, and x sub I is equal to a plus I delta x. Okay, so we're going to use it over and over and over and over and over. So for part A, what we're going to see here is we see right away, we see that a is equal to 0 and b is equal to 7. So we know that delta x is equal to 7 over n, and we know that x sub I is equal to 7 plus, oh not 7, 0, because that's our a value, plus 7i over n, because we're just taking our delta x, we're adding an I to it, so maybe another way to say it is x sub I is equal to 7i over n. Okay, so now we go to our original function here. So we have the limit as n goes to infinity of we don't need to write all this sequence stuff. Let's just go ahead and write the function. So we have 1 over 1 plus 7i over n times 7 over n. Okay, so this is our function. We're trying to pick out our delta x and stuff. Okay, so there's our delta x right there. All right, and then our x sub I, that's our delta x. And now our x sub I, okay, I see that. That's right there. That's x sub I. So now let's go ahead and rewrite this. So what we get here now is we get that our function is 1 over 1 plus x sub I, and that's multiplied by delta x. So that tells me that this whole part of the function, I'm looking at that, that's our function right there. That whole part of the function, that must be f of x sub I. Okay, and so that equals 1 over 1 plus x sub I. And so my function that I would be finding the integral of is 1 over 1 plus x. 1 over parentheses 1 plus x. Okay, let's do the same thing for part B. So for part B, I'm given that a is equal to 1, and b is equal to 7. Nope, b is equal to 8. So my delta x is equal to 8 minus 1 over n, which is 7 over n, same thing. And my x sub I in this case is different. It's 1 plus 7i over n, because we're starting, of course, at a equals 1. Okay, and then so the function that I'm dealing with, okay, so now what do we have here? We have our function given to us. It's 1 over 1 plus 7i over n times 7 over n. Okay, so let's pick out our parts. So I see my 7 over n. Okay, that's right here. So that's my delta x right there. And my 1 plus 7i over n, that's the whole bottom there. So that's my x sub I. Okay, so from here now, I see that what I get is I get 1 over x sub I times delta x. Okay, so then my answer, this thing right there, that's my f of x sub I. Okay, so that's 1 over x sub I. And that tells me that my function here is 1 over x. Okay, now that makes sense, because if we're thinking about plugging in the endpoints, what number would we get? So we're plugging in a 0 into the integrand, and we get 1 over 1. Okay, we plug in a 7, and we get 1 over 8. Now if we plug this 1 in here, we get 1 over 1. If we plug in an 8, we get 1 over 8. So that makes sense, because the endpoints are giving us the same values, which is good, because they should be the same function height, because they're the heights of rectangles. Now, part C is a little bit trickier. Okay, so for part C, our A is equal to 0 and our B is equal to 1. So our delta x in this case is equal to 1 minus 0 over n, or just 1 over n. And our x sub I is equal to 0 plus 1i over n, or you could just say that our x sub I is equal to I over n. Okay, so now if we go to our function, which is 1 over 1 plus 7i over n times 7 over n, we need to find our I over n and our 1 over n inside of there. Now, in order to do that, I need to put a 1 that's not written right there. Okay, so I have my I over n, there that is right there. So that's my x sub I, and I have my 1 over n right there. That's my delta x. So I can substitute those in. This is 1 over 1 plus 7x to the I, right? Because I have a 7 multiplied by that whole thing, times on the outside I have a 7 delta x, because I didn't use that 7 up when I was doing my substitution. Okay, and so I do need to rewrite that one more time. I need to write that 7 in there. So I get a 7 over 1 plus 7xi is times delta x. Okay. So now this part right here is my function. Okay, so it's 7 over 1 plus 7x sub I, or my function itself with just an x is 7 over 1 plus 7x, and that's what needs to go in here, 7 over 1 plus 7x. Okay, a little bit different than the first two problems. Okay, so just following the form here, these problems are a little bit weird because you're like going in reverse of the process that you would normally do if you were trying to calculate the integral. All right, let's keep chugging. Problem number 3 is exactly like problem number 2. All right, so for part A, we are given that A is equal to 0, B is equal to 2. So delta x is equal to 2 over n, and x sub I is equal to 0, so 2i over n. Okay, and then the function that we start with is 12 times 2i over n minus 2 divided by n. Now that's a little annoying because I don't see anywhere, obviously, my 2 over n. So what I need to do here is I need to pull that 2 over n out using the distributive property. So let's pull out a 2 from the numerators and an n from the denominators. So that's good. That takes care of this n. Right? That's my n that I'm moving out. And then on the 2's, so I'm going to have a 1 on the bottom. And then I'm going to pull a 2 out from that 12. And then we still have the 2i over n. Remember, I want to pull out the 2 from one of the factors. And then I pull out the 2 from the negative 2, so I get a negative 1 right there. And now I do see my x there. This is my delta x. And there's my x sub I right there. So f of x sub I is equal to 6 x sub I minus 1 over 1. We're not going to need to write that 1 in there. Okay. And so my function itself right here is 6x minus 1. Okay, that was tricky. Now let's do the exact same thing with our a value being 0 and our b value being 1. So my delta x in this case is 1 over n, and my x sub I is equal to I over n. And we're going to do the exact same thing. So we have 12 times 2i over n minus 2 over n. And we're going to start by trying to pull out that 1 over n, because I'm going to pull out my delta x right there. And what's left inside of there, well, let's pull out a 1 from everything, so that doesn't change anything. So we have 24i over n. So I'm just rewriting that a little bit because I'm going to need to pull out that I over n next. So I'm multiplying that 12 and that 2, and that's just a 1 right there. So now this thing right here is my f of x sub I. So my f of x sub I here is 24 x sub I, okay, and that's because my I over n right there, that's my x sub I, minus 2, and my f of x then is just 24x minus 2. Alright, so just a little bit different way to write up these functions. Okay, let's go ahead and move on to number 4. Things get easier. Evaluate the integral below by interpreting it in terms of areas. Draw a picture of the region. Okay, so let's say that our function right here is the square root of 16 minus x squared. And so let's plug in some values here. I see that x has to be in between negative 4 and positive 4. And if I do a table of values, I get, so let's do a negative 4 and a 0 and a positive 4, and if I plug in a negative 4 and a positive 4, I get zeros, and if I plug in a 0, I get a 16. Let's try to plot that right there. Okay, so at negative 4 and positive 4, we have zeros. Oh, we don't get a 16 there, we get a 4 right there. Sorry, everyone. So we get a 4 right there, so that's 4, and that's negative 4. And of course, that's because, let's look at this another way. Y equals 16, square root of 16 minus x squared. If we square both sides, we get y squared equals 16 minus x squared. If we add the x squared over, we get x squared plus y squared equals 16. And 16 is the same thing as 4 squared. And this is just a circle with origin 0, 0 with radius 4. Oh, so this is a circle right here, which makes sense why this problem would say geometry. So this is just a half of a circle, right? So half pi r squared. So my answer here is half pi, and in this case my r is 4 squared. So that's 16 times, so 1/2 pi times 16, okay, because that's 4 squared, and so 8 pi is my answer. Okay, not too bad. All right, next problem here. We're doing the integral of an absolute value function. All right, absolute value function. I know that this thing, 4x minus 9 equals to 0. I'm trying to find my 0 here. So I have that x is equal to 9/4 or 2.25. Okay, so 1, 2, 3. I have a 0 at 2.25, and then I probably want to calculate my endpoints as well. So let's calculate f of 0 and f of 3. F of 0 is positive 9. F of 3, 12 minus 9 is 3. So there's 3 right there. And, oh, I didn't do a very good job. I guess that's 9 right there. Okay, so we're doing this area given underneath this absolute value graph. And I see I have 2 triangles here. Okay, so now remember, this point right here is x equals 9/4. Okay, so the area of this first triangle is 1/2. The base, in this case, is 9/4. Okay, and the height is 9. And remember, I got the height by plugging in x equals 0. Okay, and the base I got because that is the 0 of my absolute value function, so that's where it hits the 0. Okay, so that's the first one. And then the second area is 1/2, and now the base in this case is 3 minus 9/4, right? And that's because like we have from 0 to 3, and we stop here at 9/4. That's the first. This 9/4 is the first length. Well, what's this length right here? Well, that length is 3 minus 9/4, right? Okay, so that's the base. And now the height. That height, we said that was a 3. This is at the point 3, 3. Is that right? Yeah, that's at the point 3, 3 right there. So the height is 3. So then our answer here is just going to be, I don't know, what do we want to put here? Let's just do that as our answer. Let's do 1/2 times 9/4 times 9 plus 1/2 times 3 minus 9/4 times 3. And Webwork will take that. All right, let's keep on chugging. All right, now for problem number 6, we're actually going to go in the forwards direction. We're going to calculate this integral using a Riemann sum. Okay, so first of all, what we have here is we have that a is equal to 3 and b is equal to 8. And so delta x is equal to 8 minus 3 over n, or 5 over n, and x sub I is equal to a, oh, we know a is 3, plus I, and in this case delta x is 5 over n, so that's the same thing as saying 3 plus 5i over n. Okay, and now we know from the definition that the integral from a to b is of f of x dx is equal to the limit as n goes to infinity of the sum I equals 1 to n of f of x sub I times delta x. And in this case, we are going to just substitute in. So our x sub I is 3 plus 5i over n. And our delta x, of course, is 5 over n. And that is exactly what we need to plug into our function. So our function is given to us. Our function is, of course, that 2x minus 9 integrand. That's our function right there. So we're just going to plug 3 plus 5i over n in for that x right there. We're going to subtract 9. So that is our f of x sub I. And then we still have our 5 over n. And then simplify this just a little bit. So we have the limit as n goes to infinity, the summation I equals 1 to n, and in here we're going to get 6 plus 10I over n minus 9 times 5 over n. And so that ends up being exact same thing here. And we end up with a negative 3 plus 10I over n in there, multiplied by 5 over n. And we're going to go ahead and need to distribute that 5 over n. And when we do that, that should be an n up there, we end up with negative 15 over n plus 50I over n squared. Okay, and that is exactly what we're going to put in there for part A. It's negative 15 over n plus 50I over n squared. All right, now the finish of this problem is a little bit faster. All right, so now what we can do is we can convert our series, our summations. We can pull out the constants from each one of these terms. So we get a negative 15 over n summation I equals 1 to n of 1. Okay, there's no i's in there. And then we can pull out a 50 over n squared right here. And then we have the summation I equals 1 to n of I. All right, now the reason that we want to do that is we can use our summation rules on equation 1 and equation 2 right there to rewrite these summations just in terms of n's. So you have negative 15 over n, the summation of 1 is n, and 50 over n squared, and the summation of I is 1/2 n squared plus 1/2 n. Okay, and now if we go ahead and distribute that a little bit, we get the limit as n goes to infinity of negative 15 plus 25 over n, which is just the limit as n goes to infinity of 10 plus 25 over n. So that's what we're going to put in for part B. So that's 10 plus 25 over n. And then when we take that limit, of course, we just get 10 plus 0, which is equal to 10, because that 25 over n term zeroes out. All right, it's kind of a drag. Luckily, we have to do the exact same thing in problem number 7. So let's go ahead and get started. All right, let's get some of our stuff laid out right away. So we have a is equal to 0 and b is equal to 5. The a's and the b's given to me. And so delta x is equal to 5 over n, and x sub I is equal to 5I over n. And so then we have that the integral is equal from 0 to 5 of 3x squared plus 4. Okay, so our function is 3x squared plus 4. Okay. So now using that formula, we have that this integral is equal to the limit as n goes to infinity of the summation I equals 1 to n of f of x sub I delta x. And so if we substitute this in, we have the limit as n goes to infinity, the summation I equals 1 to n, and our f of x sub I is going to be 3 times 5I over n squared plus 4. Okay, so what I did there is I took my f of x and I plugged my x sub I in for my x, and then my delta x is 5 over n. So if I want to simplify this at all, I have the limit as n goes to infinity of the summation I equals 1 to n. And what do I get in here? So I have 3, and then this turns into 25I squared over n squared plus 4 times 5 over n. So I could rewrite that 3 times 25 as a 75 right there. And this is part A. So for part A, I get 75I squared over n squared plus 4, make sure that's in parentheses, times 5 over n. Okay. Now, what I'm going to need to do is I'm going to use my series rules, again, from part number 1 right here. And the series rules that I need to use are going to be the I squared and the 1 series rule. But before I do that, let's do some simplification. So we have the limit as n goes to infinity of the summation I equals 1 to n, and I'm going to multiply that 5 over n to each one of these terms. And so 5 times 75 is, oops, I don't know that one off the top of my head, 5 times 75, 375, so I get 375 I squared over n cubed plus 20 over n. Okay. And so I'm going to pull out my I squareds and my 1s and stuff. So I have the limit as n goes to infinity, summation I equals 1 to n. Oh, I'm going to distribute here. Okay, so I'm going to pull out a 375 over n cubed, and then I have the summation I equals 1 to n of I squared. And then I'm going to pull out the 20 over n, and I have the summation I equals 1, that's a 20, to n of 1 right there. So that's my I squared, and that's my 1. Okay, and so I'm going to need my equations for what my summations of I squared and 1 are. So if I go up here, I can grab my equations that are given to me, and that show me another example thing. And so when I do that, the equations that I need right here are that my I squared, so I have 375 over n cubed. My I squared is 1/3 n cubed plus 1/2 n squared plus 1/6 n. And my 1, so I have 20 over n, is just n. So that's equation 1 right there, and equation, well, I guess this is the one that I labeled as equation 1, and that's the one that I labeled as equation 2. But you need to use those equations nonetheless. They're the equations for the summation of I squared and the summation of 1. We're going to delete that because I need that space later. Okay, so now what we need to do is we need to simplify this beast. We're going to need to go on to a different piece of paper right here. So we have the limit as n goes to infinity of, now what do we get in here? So what's 375 over 3? That's just 375 over 3. Okay, that's my n cubed terms. And then I get 375 over 2n plus 375 over 6n squared. And what I'm doing here is I'm multiplying this term to each of those 3. And then I have a plus 20 left on the outside. Okay, and so this is my answer for part B, right there. And then part C is going to be 375 over 3 plus 20. Once I finally evaluate those limits. And I promise you this is the last problem like this in this problem set. We have 3 more quick ones to go. Let's crank them out. Okay, problem number 8, we're trying to do something pretty simple. We're just trying to use the definition that integrals are additive, and we can use this example to calculate that. This is, you get to this example by clicking that see a similar example on Webwork, but there's an easier way to do this. Okay, let's say that we have this integral from 8 to 20 of some function. Okay, that's this thing right here. That's that whole integral from 8 to 20. And then we're subtracting off the integral from 8 to 11. What are we left with? Well, we're left with the integral from 11 to 20. Okay? And let's use that exact same strategy here for problem number 9. Okay, so problem number 9. So we have our number line here. All right. It says that the integral from -4 to 5, that whole integral right here is equal to 4. And then the integral from -4 to -1 is equal to 19. And that the integral from 2 to 5 was equal to 6. And so they want to know first in part A, what does the integral from -1 to 2 look like? Okay, that's a little bit weird. Now, what number do we have to put right here so that 19 plus A plus 6 is equal to 4? Well, that's an easy algebraic equation, right? We have 19 plus A plus 6 is equal to 4. So A is equal to 4 minus 6 minus 19. So A is equal to -2 minus 19, -21. Okay. Now, another way that we could have solved that is we know that the integral from -1 to -4 of f of x dx is equal to -19 if we flip it. And if we add to that the integral from -4 to 5 of f of x dx, we know that that is 4. And if we add to that the integral from 5 to 2 of f of x dx, we know that that integral is -6. I know to flip that because I have the integral from 2 to 5, and I need the integral from 5 to 2. And if I add all of those numbers together, I also get a -21. Okay? Kind of think about it as like a path through the integrals or something like that. Now the integral from 5 to -1 is just the opposite of the integral from -1 to 5. So you can say the integral from -1 to 5 of f of x dx is equal to -21 plus 6, so -15, which means that the integral from 5 to -1 of f of x dx must be equal to 15. This is just a numbers game that's showing how integrals are additive because it's like an area that we can add together. A little bit weird. Shouldn't be too hard. Last but not least, a really easy problem that looks really complicated. Okay, so we're doing x from -6 to 5. Okay, and then our f of x function, let's do the axes right here. That's our f of x function, and that is bounded in between 2 and 3. Okay, and so our function is stuck in between 2 and 3. We do our blue function here. We don't know what it does, but it kind of bounces around in between 2 and 3. And now we want to know what is the minimum and the maximum area. Well, the minimum area that f of x could have underneath it is just the minimum part of the function. So 2 times, I mean, this is technically 5 minus -6, but it's just 2 times 11 because that's the width of the interval. So the minimum is 22, and the maximum is 3 times 5 minus -6, or 3 times 11, or 33. Okay, and the maximum, of course, would just be the area if it was at 3 the whole time. So you just take the width, in this case the width is 11, and you multiply it by the lower number to get your minimum, and you multiply it by the upper number to get your maximum. And that is how you grind through the 4.2 web work. Good luck. I hope you have a restful break next, or you're just getting over a restful break, and let's finish off the semester strong. Sorry this 4.2 web work is such a bugger. Good luck.